to scroll.
Gotcha.
Okay.
No problem. All you. All right. Prepare your tutorials.
Is text legible or should I invert the colors?
A slightly bigger font might be nice. That's better.
Yeah. So this is going to follow from the tutorial from yesterday. So it's going to use the same cactus installation. So make sure that's all set up. This session is going to be about writing a thorn from scratch. A thorn essentially being a module in cactus. So if you need to do something or run some kind of simulation that a pre-existing thorn can't do for you, we're going to be writing a thorn. So a thorn has a few things. It has a name. It has to live in an arrangement. So cactus, in your cactus folder, you're going to have this arrangements directory. In there, you have directories of arrangements, and in those arrangements, you have thorns. Each thorn has 4 special configuration files. You have interface, schedule, param, and configuration. The source directory where all of the C, C++, or Fortran source files live. And then you have a make code defen file, which is like a make file that lists all your source files. So this is just some magic stuff for us.
Make sure, if you want to follow along, make sure you have the Thorn heat equation notebook open. You should have that in your account.
Yeah. And the Thorn writing is evolving a basic heat equation. I should have said that. So in this cell, we're just saving the home directory and cactus directory as variables. And here we're specifying the Thorn name, which is heat equation. And we're going to put it in an arrangement called tests. So in the cactus directory under arrangements, we're going to have tests, and under tests, we're going to have the equation. And that directory, we're going to have all our stuff. If you want to start over at some point, you could have comment this line to with everything we did. This cell is going to make all the directory. So we have source for the source files. We have test for tests. R, you can put R files here if you want. Doc is where you put your docs. First file going to make is just a README. You can replace your name and email in these fields if you want to. Directly again. Okay, so here's what we're trying to evolve. We have this simple heat equation here with one dependent variable u, and we also have this parameter alpha that we're going to add as a runtime parameter set in a par file. Here's that same thing written as a lag difference. We have these boundary conditions. We're just going to make everything vanish at the boundaries. Boundaries are all zeros. And we want the initial configuration to this. So first, we're going to make interface.ccl. There's a few things that are happening here. I'll just start from the top. So first thing, inherits grid. This is saying that we want to be able to use variables from the grid Thorn. And the reason we're doing that in this case is because we want the X, Y, and Z variables. Because the initial condition, initial configuration depends on X, Y, and Z. So grid is where we get those from. Implements heat equation. This is setting the Thorn's implementation name heat equation. This is the name of the Thorns where we used to refer to this Thorn. In this case, it's just the same as the Thorn's name. And down here, we're declaring our variable. We only have one variable, u. So what this block is saying is we have a variable group, because all variables must be in a variable group. This lets us declare many variables at once, all with the same properties. We have a variable group called eval group. Variables inside this group are grid functions, which are distributed 3D arrays. And these arrays have points that are real numbers, and they have 2 time levels. And then we're just saying that we have one variable in this group called U. And the reason we need two time levels is because when we're evolving this, you can see the value of any point is dependent on the value of that point in the previous time step. So we have two time levels that we have the current time set and the one previous. So what this will do for us in code is when we say time levels 2, that means we'll have U available and we'll also have U underscore P, U at the previous time level. If we want more than two time levels, it will give us U underscore P, and so forth. Those zones, these were covered yesterday, so I'm not going to spend too long on this part, but essentially when you split up the grid across several nodes, if you're on the boundary of where that split happened, you're going to need to get the data that would be there from another node. So Cactus will do this for you, but we need to tell it to. We'll get to that in a minute. But Cactus considers ghost zones and boundary zones different. So while the ghost zones will be handled for us, we have to explicitly handle the boundary conditions. The boundary being not the boundary between a part where the grid was split, but just the edge of the grid. Next file is schedule. So in schedule, we are telling Cactus when to run all of our functions. Every function has scheduled somewhere to run in some bin. So in this example, we have two bins that we care about. We have initial and evolve. Initial runs once at the beginning, and this is where we're going to initialize the state of the grid function. And then evolve is going to run every time step, and that those functions are evolving one time step forward. Because the Euler method is good enough for this system, we are using evolve, but if you wanted to use a more complicated time indicator like Thorn, you would instead use the Thorn, and that gives you a different bin that you have to use. In this case, we're fine using evolve. So we're going to have three functions. We have initialize, update, and boundary. Initialize will initialize our grid function. Update will evolve one step forward, and boundary will handle boundary conditions. And we have one variable group, evolve group, because U is in this group. So in this in the schedule file, we're also going to allocate storage for it. Here's what that file looks like. Here we're just saying allocate storage for evolve group, and this 2 in brackets for allocating storage for 2 time levels. Because we're not doing anything complicated, we just want to allocate storage for both time levels. Here we are declaring our functions and scheduling them. So first we have heat equation initialize. We're saying to run it in the initial bin. Laying C means that it's in C or C++. Writes and reads. So writes is saying that this function will write to the U grid function and it will write to every point. And the reason we have these declarations is because it lets us do some optimizations, but it's also good for error checking. Cactus can detect if you're doing certain things wrong. You can improve these. We're saying we read grid coordinates. Remember, we need to read the X, Y, and Z coordinates. That's stored as one coordinates variable in the grid form. And because it's from a different form, we have to fully qualify the name. And we're reading it everywhere again. Here we're saying we're running the update function in the evolve bin. Again, it's written in C or C++. It's writing to the interior of U, not everywhere, because we're not writing to the boundaries in the update function. We're doing that in the boundary function. And reads U sub P. So we're reading the previous time level of U, but at every point.
Why does it only write into the interior?
Sorry?
Why not write it everywhere?
Because this is a stencil function, so we can't write to the boundary in the update function because it's depending. Each point is dependent on its neighbors. And because there are ghost zones, we might not have all the neighbors. Point. So we might put the boundary in the next function, the boundary function. Right? We're scheduling it in the same bin after update. So here we're writing to the boundary of view. And sync, this is saying that we want to update the ghost zones at this point. So sync evolve group means update the ghost zones for anything in this group. Here's param CCL. So this is where we're going to declare all of our runtime parameters. This is anything that we would declare in a par file. In this case, we have one. We have this thermal diffusivity constant. It's a real number, and we're calling it alpha. Here, we're saying the range of values that we have with this syntax. So this is saying anything from 0 through anything. So any positive value will be accepted. And then down here, we're giving a default value of 1. So if alpha is absent from the par file, it will default to 1. And down here, commented out, we have a few different examples of different types of parameters. Keyword parameter is a string with a set of allowed values. String and specify a regex that specifies what values are allowed. We have booleans and integers. In this case, we only have this one alpha. And then finally, we have configure.ccl. In our case, it's just going to be empty. There's a few things you can do in this file, but for example, if you want, if you need npi.h, we'll put that here. Any questions about the CCL files? Okay. Now we're going to move on to our source files. First, we're going to write the init function. Write it in Thorn directory /source/init.c, and that looks like so. There's a few boilerplate things we always need. We always need cctk underscore arguments in the argument list. And we always need these two macros here. We have declare cctk arguments underscore function, and then declare cctk parameters. So these respectively will bring in things we declared in interface and param.ccl. And here we have just a 3D loop. We're looping over every point in the grid function. This variable here, cctk underscore lsh, this gives us the size of the dimensions, right? So cctk underscore lsh of 0 is the size in the x direction, and 1 and 2 are the y and z directions. So these are the boundaries for these loops. And inside, remember the initial condition is this equation. That corresponds to what we're writing here. So even though we're conceptualizing these grid functions as a 3D shape, internally Cactus they just keep all of the points in a 1D array. So if we want to index into a grid function, we need to sort of swizzle these 3 indices down into one linear index. That's what this function, g@index3d, is doing. You pass the grid hierarchy and then your 3 indices, and you get one index. And we're setting u at that index to this expression, which is just the initial equation. Now we have evolve.c, which is going to have the update function. The boilerplate is the same. So what we're doing here is, first we're getting the number of ghost zones on each side of each dimension. So, number of ghost zones in the z, y, and x directions. We're getting the t, we're getting the x, y, and z, and another 3D loop. And this time we're not starting at 0, ending at LSH of whatever index, because we need to skip the ghost zones. Remember, we're only writing to the interior of the here, so we need to skip the ghost zones, and that's how you do that. And then this internal, this part here, most of this is just getting those linear indices because to access all of that point's neighbors. And here we're just calculating the kind of difference and then setting it.
Yeah,
So, right here, this is just going through with the points in one binary frame. It's not the all points.
There's only one grid function U at this point.
yeah, but what he's asking is, he's asking if this were mesh refinement, Cax would just repeatedly call this on the refined levels for you. So you don't have to think about anything but this.
Here we have boundary.c, which is going to have our boundary function. This one seems long, but it's really just doing the same thing 6 times. So we have this CCTK box thing, and what this will do is it will tell us whether the piece of the grid function we're currently on, whatever machine this is, has has a boundary in a certain direction. So for example, CCTK box of 0 will tell us whether we have a boundary in the lower X direction. And if we do, we want to set all of those boundary points to, in this case, we're saying it's 0. We're doing the same thing for the upper X, lower Y, upper Y, and so forth. It's the same thing, it's just which boundary we're setting. And so in all these cases, we're setting the boundaries to 0. And we're not doing anything explicitly to the go zones because they're this function to same evolve groups, so the go zones will be handled for us here.
Are those the boundary points? Don't they have those? Are those stuff?
So the boundaries and the ghost zones are distinct. So the boundary is where the grid ends. There's nothing beyond it. And the ghost zones are the boundaries. If you have two nodes and you're splitting up the grid function between those 2 nodes, and say I'm on the edge where the split has happened, and I need to get data from over here. That's a ghost zone. Right? We're copying data back and forth.
But an actual boundary itself. Right.
Well, it depends on what we're saying the boundary condition is, but we are saying, right, we're explicitly saying the boundary condition is just setting it to 0. Everything vanishes at the boundaries. If you wanted it to, have some other behavior, you might have to write that yourself in the boundary function. Yeah, you could you could have in your brand.ccl, you could declare a keyword parameter and list all of the possible boundary conditions 1, and then in your boundary function, you would just, if you have access to those parameters, if you have this macro, so you can just read that and decide what you want to do. Actually, that's one of the exercises at the end of this notebook is to do that yourself. So 3 source files, init, evolve, and boundary. Those are going to have all of our functions that we wrote. And so now we just need to make our makeable happen, listing all the source files. If we have subdirectories, we put them here. Now our Thorn is written. Now we just need to add it to our Thorn list and then rebuild Cactus. So here we're just listing the Cactus directory. The Thorn list for our current configuration is located in Cactus config, same Thorn list. So all we're doing here is just adding the name of our Thorn, arrangement included. We're adding that to Thorn list. Here we can see table of the Thorn list now includes tests stroke heat equation. That's our Thorn. Now that we've done that, we just have to rebuild Cactus. Build. I haven't skipped any cells, it will work. Let's go. Are there any questions so far? Excellent. Oh, yes.
So, when you initialize, you don't have to specify any zones.
Well, so we actually are writing to the go zones. So you look in, say, right. So here in update, you see we're getting the number of go zones in each of the directions, and in the loops we're actually skipping them. Right, we're starting K at GZ and then ending at LSH minus GZ instead of starting at 0, we're just ending here. But in initialize, we're not doing that. We're not skipping the go zones, so we are setting everything.
You always have to do that.
Yeah, you do need to initialize things. Yeah.
But in, so in principle, you could initialize the interior and then call it sync. But because this is an analytic function of X, Y, and Z, you don't need to do that.
Generally, it's safely.
Yeah, the sync
So,
should be
yeah,
more.
so I'm gonna wanna write it in.
So this is slightly more optimal. Probably have trouble measuring how much you save, but.
Yeah, it's just initialize.
Right.
Yeah. Okay, cactus is built.
Oh, good.
Yeah.
So now we're going to try to actually run our calculator. We'll make a part file. Not going to spend too long on this because most of these were covered yesterday. Just setting up basic things. Down here though, we're saying we're going to output the equation U variable that we made. We also want to output coordinates every really big number because that's just how you print it once. So some factory to create and run the equation simulation, give it the part file we just made. And yeah, in the par file, of course, we have to activate our Thorn. And so we just say active Thorn's the equation, and that's going to schedule our functions, and they'll just run for us. Down here, this code really, we should rewrite this to use tweebit, and currently it's not use tweebit. I'm not going to spend too long on details, but we're essentially just processing the HTF5 output to measure it. The output's going to be in the simulation directory, the name you gave, output 4 zeros, and the equation. We're doing some Python stuff. That, isn't that something? Animation of the whole solution.
Blink, you'll miss it.
There we go. Isn't that great? Yeah. So our Thorn works. Here at the bottom, we have a few exercises you can try on your own. Change the time step size and the termination time, change the grid size and the grid spacing, change the position and height and width of the initial pulse, add some new boundary conditions, maybe add a parameter to set the boundary condition. This one, number 6, we already did that. That's the end.
So, one of the things we thought you might want to do at this point is, take a look at the exercise, run the code first, make sure get all the output we got. And then, you can try the exercises and see if those work for you. And, we can give you help if you get stuck or whatever. And, are there other questions about this whole process? There don't seem to be any. I may have allocated too much time to this. So, if you.
We could run the exercise.
Yeah, but you're supposed, the concept of the exercise is you're supposed to try to figure that out on your own.
Yeah, we feel miserably here.
Yes, yes, that's the idea. All right. Okay. Let's thank the speaker. Grail. Sam Cup is going to talk about Grail.